Hello, my name is Rohan, and I'm an incoming second year at the University of California, San Diego, studying computer science. And today I wanted to discuss my project for the Music 7 class, which is machine learning for denoising audio. As an introduction, I wanted to explore, like as the name suggests, how machine learning can be used to remove noise from audio. And I also wanted to integrate software engineering by deploying a web application where the user can upload a recording and then get back a denoised version of that recording, where machine learning models have been applied. And so here are some links. I was able to upload this project. And the front end, which the users will interact with, is through Vercel. So you can see that here. And then the back end of the application, which is like the server that does like a lot of the machine learning on from behind the scenes, is this site here. And the root directory is just the simple hello world screen as just kind of like a check that it's working properly. And this contains like some upload and download routes that are basically called by this front end application. So when we upload a file and we hit upload and denoise here, then it'll make some calls to the backend server. Although we don't really see these calls do happen. And that's discussed a little bit in the next slide. I also have my GitHub link here where we can see the code that I used for this. And then there's some screenshots of the backend and front end. And then here's a simple overview of like how the application works. So the front end website, which is through here. This is the front end website. It sends a post request to the backend to upload the audio recording. And then the backend server will apply various like machine learning models to denoise the audio. And then in the response to that like post request that was made, the backend server will return the denoised audio file itself. And then this denoised audio is also stored in the backend so that the front end can make a GET request to later retrieve a download of this audio. This is the workflow. And it's a pretty simple setup, I think. Continuing, I thought about this project like in terms of two types of noise that I'd be interested in removing from an audio. And one of those is the uniform low noise, such as with the fan noise moving throughout the music performance. So if you have like a fan in the background, while there's different musical instruments being played. And then you also have occasional high noise, which is like someone sneezing in the middle of a performance, right? And of course, if we have like what would be considered high noise throughout the recording, then at that point, that should just be considered a signal, right? So it would really only be reasonable to consider noise in the form of like this uniform low noise that's throughout the recording, or occasional moments where there's incredibly like high noise, like someone sneezing. So that was very reasonable to sort of divide and conquer the problem of denoising audio in these two parts, uniform low noise and occasional high noise. And so for high noise, um, after trying out like the one class support vector machine and local outlier factor methods from the scikit-learn, I eventually decided to stick with the isolation forest because of the runtime improvements and also due to various tests. And isolation forest is largely based on ensemble methods and binary trees in order to detect outliers or anomalies within the data set. As we can sort of see in this like slide, that it's able to use binary trees as sort of like to make to implement like a scoring algorithm, I should say. It's to implement a scoring algorithm. And so it implements, so it finds the outliers this way. And this is targeted towards the high noise aspect. Because it's able to like look at the digitally sampled audio and then be able to find like outliers within that like array of digital samples. And then for low noise, I think that's actually a lot harder than doing like high noise because if we just have occasional high noise in a recording, then we just have to find the outliers in the digital samples. But for low noise, we have to take like a different perspective on like the data set entirely and convert it into like more of a window framed version. But anyhow, the techniques that I looked at for low noise included like principal component analysis. I included the kernel version of the principal component analysis as well. I also tried setting up LSTM-based autoencoder and normal autoencoder. And I guess the whole idea kind of with all these techniques, in some sense, is that you're trying to take your original data and create like a reduced dimension representation of that data, right? And so we can see that sort of in this picture with the encoder, creating a reduced representation of the data. And then using that reduced dimensional representation, we want to try to reconstruct the original data from that through the decoder here. And so once we have our reconstructed input, then we want to try to take a loss function between our input and our reconstructed input here. And we want to try to minimize that loss function. And using this type of technique, we can reduce the noise within the data, especially like if we average out with the reconstructed input. And what I ended up using was a technique known as the fast independent component analysis. And so this is using this is to separate a multivariate signal into additive components. And assuming that like one of the subcomponents is Gaussian in order to do this. And the reason that I eventually chose this technique as opposed to like principal component analysis is that it was like previously used for estimating sources from noisy data in a blind source separation task. And I would also say that like using an LSTM-based autoencoder and normal autoencoder, these are both very like computationally expensive approaches. And I realized this like when my model was like hanging during the training loops a lot, and I wasn't able to complete like the training very well. But I'll speak a little bit more on this later. So continuing, I used this fast independent component analysis, and the study that kind of motivated that was this here, which is from scikit-learn, but there's the fast independent component analysis blind source separation. So you can see a little bit more information like on this website. But it was estimating sources from noisy data, which is, I guess, what we're trying to do here as well. And so it generated some sample data, and then they tested it using PCA and fast ICA. And these are like the various results from like the study. And qualitatively, it seems that ICA actually recovered a lot of the desired features, a lot of the desired source features in this case. And it also had very fast running time. I guess using PCA and using fast ICA, but I guess this was just what they're simulating data. But I still think it was a pretty good runtime for this task. All right, continuing. The final in the final result, if we upload like 30 seconds of audio, it'll take like 70 seconds to denoise. So it takes like just a little over like probably 2 seconds for every like input second of audio that we give it in order to denoise. And I think that the most expensive step of that would be like isolation forest because there's such a large array of digital samples. So of course, one way that we could speed this up would be to take our input data and actually downsample it using Librosa. And this isn't something that I implemented yet, but it would be like a reflection as like the next step that I would take to improve the application. And then in terms of other like future steps that we could take is that we can check that the user uploads like maybe like a very, very large recording. We should maybe throw an error message because it would take a very long time to denoise, for example. And then of course input type checking. So currently my the uploading doesn't like check what type of file goes in. And it'll probably just throw a separate error if there's like a bad file type. Like, I don't know, putting like a PNG or a JPEG type image instead of like an audio recording. There's no like separate check to prevent the user from doing this. So I didn't account for this in my project yet, but this would be like a separate an improvement for the future. And then similarly, it would be better for the user again if we had like a progress bar whenever they uploaded their recording. And then we also had a reload button as well, like because you need to reload the page every time to upload a new recording. And then similarly, recordings are stored in the backend, so they should be cleared at regular intervals, presumably. So if I had more time, I would use a cron job to implement that, which is basically just a way of telling Linux to do something regularly. Because my backend was deployed on something called Python Anywhere, and then it has like there's some Linux involved, so you can set up cron jobs to do it. And also we could like set up an LSTM network, but this is more in like in a supervised context. So if we used a supervised approach instead of an unsupervised approach to handle the uniform low noise, then what we could do is we could look at a data set of recordings, of very clean audio recordings, and then we could introduce various sources of like Gaussian noise and other noise within those clean recordings, right? So we set the noisy recordings as input and the clean recordings as labels in that case, right? And so we would have this LSTM network, and then this could train over a few days to learn how to denoise the audio in that case. And then eventually, the result of that process would be a series of the saved model weights. And we could load in those saved model weights. when I'm deploying the model in evaluation mode. So this is also another technique, but again, it would probably take a few days to train, so we probably didn't have that type of time for this. And yeah, we'd probably also need like GPUs and a lot more resources to train as opposed to just my weak CPU. All right. I can show some of the code that I use as well as like final results and demonstration. I think for the sake of time, we'll skip like the front end code. But yeah, there's a bit of HTML, CSS, JavaScript, and React that's used to create this page and the uploading feature. And then in the backend, we have like I guess this is the main like machine learning sort of code where we're able to like load in the audio file. And then it's like so the Y value here is just like an array of digital samples. And then we compute like the mean of the array. And then we reshape it for use with the isolation forest, right? So here we can see the use of isolation forest. And then what this piece of code is doing is that if an outlier is detected, sorry, so this code, if an outlier is detected, it will set that outlier to actually the mean value. So it'll set the amplitude of the outlier to the mean amplitude within all of the digital samples. That's the whole purpose of these 3 lines of code here. And then after that processing is done, we set up fast ICA. And fast ICA, instead of acting on the array of digital samples, it will act more on like a framed version or a windowed version, right? So there's actual dimensionality involved. And so this is wouldn't be known as like the buffered version of that input data, right? So we buffer the data here. And so when we take the buffered version of the data using a specific window size and hop size, then we can actually use fast ICA on them in order to take the forward transform and then an inverse transform of the data. And so it goes back, I guess, to this concept here. It goes back to this idea here. So sorry about that. So we use fast ICA there. And then once that's completed, then we want to undo our buffering process through overlapping and adding the various frames so that we can basically extract the denoised signal again. And then we can go back to our array of digital samples in this way. And then as a final step, we normalize to the original signal's volume. And then we basically write the file and save it. So that's a sort of the main logic that goes on like in the back end for denoising. And so it's very interesting this way. And so now I can give a bit of a demo. So one recording that I prepared was like a C major scale, but there's an occasional loud noise. There's an occasion, sorry. Sorry, yeah, there's a lag spike there for a second. There's an occasional loud noise that occurs in the C major scale recording. And so you can sort of hear it here. I don't know if I actually shared sound. So let me actually just reshare just to make sure that that came through properly. Yeah, I don't think I was sharing sound before. So let me try to replay that recording. So as we can hear, like within that C major scale, about like between 3 or 4 seconds in, there was like that slamming noise, right? So we want to get that slamming noise out of there. And so I can upload the same recording, the C major scale with the slam sound, and then we'll hit upload and denoise. And since that was like a 9 second recording, we're probably gonna have to wait like a good 18 seconds for it to denoise. And then again, here's where I wanted to sort of implement like a progress bar so that the user can kind of see what's going on. And for the sake of time, this will probably be the only demonstration, but we can hear it. And then, so I think there's a lot of room for improvement like with the model. So I think that it did try to handle that noise and it made some progress. Um, but there's still like a bit of refinement that can be done. And then similarly, I guess this will be like more of a longer one, but I could also look at like the fast computer typing. And interestingly enough, the model is very sensitive. So in this fast computer typing, my finding is that it usually takes away all the noise. So there's just a recording of me typing like really quickly. And if I were to put that in there, the finding is that it actually removes a lot of the typing noise. it comes up with like clean audio recording. So it can be very sensitive to that. Because if I want to just isolate the fast computer typing, it would actually eliminate most of the recording. So I think it's interesting. And then you can also try like uploading recordings to this website and seeing how it like acts on the website or how it acts on the recording, either. So yeah, it was an interesting exploration, and there's still a lot of room for improving this project. But it was really fun to build. And thank you so much for listening to my presentation on this project. Thank you.